Right, so in our last video, we introduced null space. Remember what the null space is? The null space consists of all the solutions to the homogeneous equation, AX equals 0. So if you have an m by n matrix, the null space is going to be a subspace of Rn. If you have an m by n matrix. And that's because, think about that, you're talking about solutions to AX equals 0. So your vectors, so when you got A times X equals 0, these vectors, I'm going to make them yellow this time rather than red. So if you have an m by n situation, m by n, your solutions have to be what? N by 1. So your vectors here are going to be an Rn. Yeah, so in this case, if we had two columns and this vector A, all right, you're going to have what? A 4 by 2 matrix. So your null space, all the solutions to AX equals 0 would be a subspace of R2. Number of columns. Yeah, the number of entries in the columns. Scroll, please. Thank you. 2. Let's just do another quick example. Let's say I got a matrix A here. And I want to figure out for what n is the null space a subspace of Rn? For which n? Or does it say the null space of A is a subspace of? It's going to be R4, right? R4. So the n here is 4, actually. Why? Because there are what? 4 columns. Right, this is a, what? 2 by 4 matrix, 4 columns. All right, so what else? Now let's do some exercises, some more basic exercises. What's that down there? What's that garbage down there doing on my screen? What garbage is on my screen? What garbage is on my screen? Get away, garbage. I don't want you. Okay. Dude, work. Okay, exercises. Determine if the vector u is an element or is in the null space of A. So number 1, we're going to give you a vector 1, 1, negative 2, and we're going to give you a matrix 1, 3, 1, 1, 1, 2. So we want to see if u is a solution to the homogeneous equation. So basically all we're going to do, we're going to take u and plug it in to the equation a times x. So we're going to have a times u. See if we get 0 out. So what do we got? We got 1, 3, 1, 1, 1, 2. And we're going to multiply by the vector. So we're doing matrix vector multiplication. Come on, red dude. 1, 1, negative 2. So remember how this works, matrix vector multiplication. You take what the first entry in the, what's that called, the vector, times the first column. So you're going to have 1 times 1, 3, plus. Then the next entry in the vector, 1 times the second column, 1, 1, plus. The last entry, negative 2 times the last column. 1, 2, and see if you get the 0 vector. If you get the 0 vector, then you're in good shape. If you're not, well then you're not in the null space. All right, what's this garbage down here? What is all this garbage? Don't know. All right, so it looks like I'm going to have, come on, man. What, 1 plus 1 minus 2 for the first entry, and for the second entry, 3 plus 1 minus 4. So that's going to give me 0 for the first entry. And the second entry is going to give me, 0. So yes, we got 0 when we plugged in U. So thus, U is an element of the null space. Solution. It's a solution to the homogeneous equation. All right, there's a train. Here's another. Oh, got more garbage down here to clean up. More garbage. Here's another situation. So we got another vector U. U is the vector 2, 0, and matrix A consists of 2 columns, 1, 0, 3, and 4, negative 1, 1. So is U a solution to the homogeneous equation AX equals 0? Question. Well, let's see. Let's take A times vector U. See if we get the 0 vector. I got 1, 0, 3, 4, negative 1, 1. I'm going to multiply it by vector 2, 0. Okay, so I'm going to take 2 times the first column plus 0 times the second column. Simplify that. See if we get the 0 vector. If we get the 0 vector, U is in the null space. If not, then it's not. All right, so that simplifies. What does this simplify to? That's going to be, oh, this guy zeroes out, so we're going to have just, what, 2, 0, 6. The other guy is inconsequential because we're scaling by the whole vector by 0, which just gives you the 0 vector, and you add the 0 vector to 2, 0, 6, and you get 2, 0, 6, so I'm not going to write any more. So since we don't get the 0 vector, that means thus U is not in the null space of A. All right, so we want to do one more exercise. One more exercise. We want to show that H, which is the set of all vectors of the form A, B, C, such that A equals 2B minus 3C, comma, A equals 6C minus 3B. This set, let me close that with curly braces, this set of vectors that satisfy those two equations is a subspace of R3, is a subspace of R3. Without using the subspace test, without using the subspace test. Yeah, I mean, if we wanted to, I guess we could use a subspace test, verify the 3 criteria, right? Show the 0 vectors there, show that the sum of 2 arbitrary vectors is there, and show that the scalar multiple of a vector with the scalar is there. But we don't want to use the subspace test. We want to use the fact that the null space is a subspace of Rn. Rn. So we know we're going to be dealing with R3 here. R3 because there are 3 entries, A, B, C, and a typical vector. So here we go. We're going to prove that this is a subspace of R3 by realizing this is the null space of something. So let's just say note that, come on, it's not writing well. Note that H is the following set of vectors. It's the set of all vectors A, B, C, right? Those are in R3. Such that A equals 2B minus 3C, comma, A equals 6C minus 3B. Here we're assuming A, B, and C are real numbers. I'm not writing that, but we're assuming that. All right, so what's this equal to? Well, let's rewrite our vector ABC as ABC. And now let's write our two equations where we get the 0 on the right-hand side. So I'm going to get what? Subtract 2b and add 3c to the right-hand side, or to both sides of the first equation. We're going to have an equation, what? A minus 2b minus 3c equals 0. That'll be our first equation. Comma. Then we'll have a second equation where we get everything on the left side and 0 on the right. We're going to have what? A. Now let's put things in alphabetical order. Plus 3b minus 6c equals 0. Okay. Nice, nice, nice. So now we can rewrite that system of equations, right? We got two equations and three variables. So I'm going to have, this is what the set of all ABCs, elements in R3, vectors in R3, such that I can write this as a matrix vector equation, a matrix vector equation. Those two equations, we can write that system as a matrix vector equation. So first, we'll write down our capital matrix A, which is going to consist of the coefficients of the variable. So you got a 1, 1 in the first column. The second column, you got -2, 3. Third column, you got what? -3, -6. Now, what are you going to have in your place of your x? Your place of your x. Rather than writing an x here, let me put that in, I don't know, I'll put it in purple. It's not writing well. It's not writing there, right there. That's going to be my vector x. Normally that's called my vector x, right? So we have capital A is the matrix that has blue entries, right? I'll make it a blue matrix. That's your capital A. So vector x is going to be purple. That's going to consist of the entries, right? A, B, C, A, B, C. So the variables go in there. And then the right-hand side of the equation, I'll call those zeros. Zeros. They make up the 0 vector. So what do we got? We got AX equals 0, right? The blue matrix is the capital A. The vector x is the purple ABC. And the 0 vector is, well, the yellow vector. So we have AX equals 0. So basically we have all solutions. That's what this is saying. All purple solutions, A, B, C, right? All purple solutions to AX equals 0. This is just a fancy name for the null space of the matrix blue, right? This is the null space of 1, 1, -2, 3, -3, 6. So we have just shown that H is actually the null space. It's just the null space, right? It's all the solutions to this linear system, this matrix vector equation. And we know that the null space is a subspace of R3, right? Because you got 3 columns here. So therefore, H is a subspace of R3. So that's a really kind of elegant way to show this is a subspace of R3 without having to go through the subspace test.